In the next example, we're going to have an equivalence relation, and we need to figure out what the distinct equivalence classes are. And it's a really nice one. We're in R squared. So A comma B means A and B are both real numbers, and C and D would be both real numbers. And they relate to each other in R squared if and only if A squared plus B squared is equal to C squared plus D squared. So if you're an element in this, in R2, if you're given any two ordered pairs, they relate to each other if and only if the sum of the squares of their components added together would be equal to each other. So describe the distinct equivalence classes. Well, if you can't picture in your head already what it is, and I don't expect you to, but you might if you think back to trigonometry and geometry. Let's just do an example. Let's make up some cases where we know they're equivalent, or they relate to each other, I should say. 1, 0, and 0, 1. If you square them and add them, you get a 1. Square those two and add them, you get a 1. And we have a couple more. 4 points right there. They're all related. They're all in the same equivalence class. Can you think of any more? Well, I know you can think of more if I start you off with, a diagram. There, I just plotted those 4 points. They're all equivalent to each other. Well, what about this one? Radical 2 over 2, radical 2 over 2. That's like a 45-degree angle on the unit circle right there. And we could get 3 more points by either adding a negative here, or a negative here, or a negative on both of them. Roughly speaking, those points. And you can do the same thing with radical 3 over 2, comma 1/2, or 1/2, comma radical 3 over 2. Remember, you can put a negative, we just defined 4 more here by just putting negative signs in, 1, 2, or both. Here's one, put a negative here, here, or both. So you end up getting the unit circle. So this equivalence class, when A squared plus B squared is 1, gives you exactly the unit circle. If A squared plus B squared is equal to 2, well, then you get a bigger circle. Or 1/2, you get a smaller circle. So each one of these circles is a set of infinite points, but each one of them is a distinct equivalence class. So notice that in R squared, if you took the union of all of these possible circles of different widths, you would get the entire R squared, the entire xy plane. You'd even have to take the case where A squared plus B squared equals 0 to get that dot is not a circle, but you get the whole R squared if you union all of them together. So we'll look, and one more thing, just because we're going to talk about this on the board behind it. Not only does the union of all of those circles give you the R squared, but no two distinct circles has a single point that intersects with each other. For example, this circle and that circle, they don't intersect. And it doesn't matter how close you get, those two circles don't intersect, don't have any intersection. And we'll talk about that again in a minute. Okay, here's an equivalence class theorem. I might prove 1 or 2 of them, and some of them you'll have to do for homework. Given an equivalence class where A is the set, and this is our relation operator, if X and Y are 2 elements of that set A, then X is in the equivalence class X. You can think of this as the equivalence class generated by X. It contains X and everything that relates to X, everything that's related to X. And that would be very simple to prove. oops. Since this is an equivalence relation, this is just by reflexivity, x, it relates to x. Therefore, it's in that set, because this set contains everything that's relatable to x. That was really simple proof. And maybe we'll do one more. Let's do B. The proof of B. If x is in this equivalence class that contains y, then x's equivalence class is exactly equal to y's equivalence class. First, note that x being in that equivalence class means it's related to y, because that's the set of all objects related to y. So what we would do next is, to prove this is true, two sets are equal. We usually prove that the left one is a subset of the right and the right one is a subset of the left. And that's what we'll do. And in order to prove that this is true, I'm just going to say let A be an element of X. The equivalence class generated by X, I guess I should say. And now I need to prove that Y is in this. Well, since this is true, by definition, A relates to X. But we also know X relates to Y. So one more line. By transitivity, because we are talking about an equivalence relation, A relates to X, X relates to Y, so A relates to Y, which means A is in Y's equivalence class. So pretty simple proofs, usually just using definitions or properties of subsets of sets. And then I think C, D, and E are probably, I'm going to leave for homework for you. I think you'll find that E you can prove simply by using C and D. Well, at least state them. X's equivalence class is equal to Y's equivalence class if and only if they are related to each other. That makes perfect sense. Remember I said that if they're not the same, this is part D, if they are not the same, then these two sets share no elements in common. If these are not identical, they have nothing in common. If they're not equal to each other, then the intersection of X and Y's equivalence classes is the empty set, just like those circles we talked about. And then to prove this one, you take every element of A and look at its equivalence class. You'd end up getting some repetition there, so you don't want to repeat them as a set. But this set is a partition of A, because you've got a whole bunch of sets here. Going back to the circles, based upon what the radius of the circle was, you got a different radius. The union of all the radiuses equaled the entire real line, and no two of those circles intersected. So basically, and I may have shown this on a partition of a set looks like this. That's a partition that contains 5 elements. The union of those 5 elements gives you the entire set A, and none of these 2 elements has any overlapping regions, or so they don't share any objects in common. They are pairwise